you're here. And I'm very happy to be speaking to you about something that I really care a lot about, which is music and sound processing in the brain. The idea of music in medicine, and this focus is going to be on rhythmic healing. So making sense of sound. So making sense of sound is a biological triumph. It involves sound entering our ear and feeding our brain, and then our brain informing what the sound means based on what we know, what we think about sound, how we move with it, and how we feel about it. So it involves cognitive, sensory motor, and reward processes. I want you to listen to this sentence and tell me if you can understand it. This is the sentence.
The juice of lemons makes fine punch.
Now listen to the first sentence again. Do you believe me? That what we know about sound influences how we hear it. And music is just the jackpot for involving our cognitive, sensory motor, and reward networks. So music is very important for strengthening communication skills, and communication skills are important at every single stage of life. And you know that. Now, there are fads, right? Bell-bottoms and fads come and go. There's been a lot in the news lately about music and medicine and healing. And I want to put to you that this is a fad, perhaps at the moment, but it is a property of our existence that is here to stay. And I am here to talk to you as a biologist. From my point of view, there are so many reasons why music is not an alternative form of treatment, but is in fact integral to health. So there are rhythms outside the head and inside the head. Outside the head, there are sound waves that move in rhythm. There are our movements. You should know, so I grew up in a household where more than one language was spoken, and I learned Italian first, which is why I can't even speak without moving. And I grew up playing underneath the piano, so I very early on had a sense that sound was tremendously important. In our brain, there are also rhythms. So there are how the electricity in our brain patterns with the rhythms that are in the sounds and also with our motor movements. So there are rhythms inside and outside the head. And to give you just some examples, some sound waves, they occur at multiple speeds. So there are slow rhythms and fast rhythms in speech. Sentences unfold in a longer period of time than words and individual syllables. In music, there is the pulse that we tap our foot to, and then there are the individual notes and very fast things like the attack of a string or the crash of a drum. And you know, I can take a walk in the woods, and my footsteps will be working at slower time frames than my the snap of foot of the snap of a twig underfoot. So you know, you have your footsteps, your crunch of leaves underfoot, and then the snap of a twig. And these are all happening at the same time, but at multiple time scales. And of course, our brain has to make sense of these time scales and of this information, and there are brain rhythms that are occurring at these different time scales. So how do we measure sound processing in the brain? And again, so this is wonderful Renee Fleming, who is part of this Music and Science initiative, which is just really wonderful, the partnership between the Kennedy Center and because Renee is the artistic director there, and Francis Collins, who is, of course, the director of the NIH. And, you know, a year and a half ago now, Francis Collins asked his institute directors, can you see music as part of your portfolio? And 21 of the 24 institute heads said yes. But so as a biologist now, funded by the NIH, how do we measure sound processing in the brain? Well, you can see sound is going into Renee's ear, and then we can pick up that sound activity, its electrical activity, because of course electricity is the currency of the nervous system. And you can see that the sound wave and the brain wave physically resemble each other, so much so that here's the sound wave. We can play the brain wave back through a speaker, and it will resemble the sound wave. So you're going to be listening to the brain a lot in this presentation. You know, how is it even possible? Just think about the fact that as I'm talking to you now, molecules are moving in the air, and we're used to the idea of taking this movement of molecules as air pressure and transforming it through a microphone into electricity, which we can play out through a speaker. Now, we can listen to the sound, and our brain will also transform that sound into the currency of the nervous system, which is electricity, and we can take that electricity and play it back through a speaker. So I want you to hear a Rhodes piano play a little bit of funky music. Now, here's the brain's response to that. So we have a lot to work with. We have tremendous granularity and precision. And again, if you think about just a little bit about where I'm coming from, I began as a cellular biologist recording individual neuron responses in the eighth nerve and in the auditory cortex. We still have an animal model, and I've been looking for the same kind of precision and granularity that you have at the cellular level in animal models in humans, and we are really getting there. This is my favorite. Okay. So deliver sound waves to the brain, pick up the brain's response to a complex sound wave, and I like to use a mixing board analogy because we can see how good a job our brain is doing at making sense of the different ingredients of sound. Now, you know, we live in we're addicted to visual images and to visual objects. And sound, we don't think about it as much as I believe we should, because sound is invisible, as are many of the world's most powerful forces like gravity. But if you look at a visual object, it's got a shape, a texture, a color, a size. And sound also, I mean, think about it for a minute. Sound has ingredients too, like pitch and timing, timbre, phase. There are all these different ingredients that invoke different neural processes that we can measure, and we can see, well, where are your individual strengths and where are your weaknesses? And from a medical standpoint, we can think about addressing these. So we can look at the strength of the fundamental frequency, the harmonics, how stable is the response, how good is the timing. And we're talking about timing on the order of microseconds. Making sense of sound is one of the hardest jobs we ask our brains to do, which is also why if you get hit in the head, it will disrupt sound processing in the brain. And one of the things that I'm not going to talk to you about today, but check out our website, and this is work that we're very much in the thick of, is we're looking at concussion. And what concussion can do to sound processing in the brain and how sound processing in the brain is a biological marker of brain health. So each one of us has a neural signature. Here is the same person's response measured over different points in time. Here's another person. You can see that the responses look very similar within an individual. Each one of us, our brain is shaped by our life in sound, and we all have individual lives in sound. And again, this is why this is important from a medical standpoint. We are interested not so much in groups of people, but in an individual patient, an individual person. So I want you to just to listen now to 3 healthy brains processing a little bit of a hard day's night. It's one brain, another brain, third brain, so obviously there's a theme here, but you can hear that each one of us processes sound distinctly. And we have access to this now biologically. So the measure that we are using is called the frequency following response, or FFR. It's objective, it's well vetted, it's mobile, it's quick to obtain, it's repeatable, and it's uniform. You can get the same response in a baby or an older person. And I will invite you, as I will invite you several times during this talk, to visit our website. It's called Brain Volts. You will find it if you just look for Brain Volts. And on the home page, there is a demonstration of our biological approach narrated by a former NFL player. It's about 2 minutes long. So playing music, making music, is one of the healthiest things we can do for our brains. And actually, right now, I'm going to answer the question that I get most often, which is, I listen to music all the time. Does listening to music count? Well, of course it counts, but in terms of changing your brain in these fundamental ways, I like to say you're not going to get physically fit watching sports. Making music enhances sound processing in the brain, and this is something that we and others, many labs, have seen, that across the lifespan, making music enhances how people, and we're not talking about professional musicians here, we're talking about people who just regularly play music a couple times a week, but regularly. And this is something that builds up over the lifespan. We have looked at sound processing in the brain longitudinally in 2 projects, one in Chicago Public Schools, where we followed high school kids from freshman to senior year, and another out in LA, the Harmony Project, where we followed 2nd, 3rd, and 4th graders. Because, one often asks, it's the chicken-egg issue. Were people born to make music? But if you start with two matched groups, and you have one group getting music and another group having another enrichment activity, you can see what impact music has. And music has a huge impact in sound processing in the brain. I can tell you that from a biological perspective. And again, if you visit our website, you can download the articles that speak to this. So I said making sense of sound. It involves our cognitive, sensory, and reward processes. And I just want to briefly give you some examples of cognitive. Across the lifespan, people who play music are better able to pay attention to a target, to an important signal, an auditory sound, and to ignore an irrelevant sound. Furthermore, people who play music are better able to perform verbal, auditory, working memory tasks. So for you to make any sense of what I'm saying right now, you have to remember what I just said a few seconds ago and work your memory to make sense of that. Well, people who play music are better at that. This is work from Charles Lim's lab, where he had musicians improvise in a scanner, And he found that when they were improvising, and this is a very creative cognitive process, that aspects of the frontal lobe, which we know are important for inhibiting our actions and self-monitoring, these were not very active. They were suppressed, whereas other aspects of the frontal lobe that are more associated with creative activity were enhanced in terms of activity. What about sensory motor? So we need to, the idea of entrainment and rhythm, this is something that enables us to move with other people, and it's important for how we feel about the other person. It's important for our relationships. This is work that Laurel Trainer did, where she had little guys. This happens early in life, little guys bouncing in sync with an experimenter. And now the question is, is this little guy going to be disposed to help the experimenter? Now that they've danced together, is he gonna help her? So, mutual cooperation happens when we move together in synchrony, when we entrain with each other.
There. Uh-oh. Oh, no. Oopsie.
So if we could just get our heads of state to move together. I want you to see how these kids look at each other when the music starts.
Hi, girls. It's August 6th. Is that right?
Yeah.
August 6th, 2012. Daddy's gonna play them a little song while they're eating their peas.
You girls ready?
So now I get to look at all you guys, and I have sweetened up the audience. Just look at the person next to you. They will be smiling. Alex referred to this. This is Robert Sartori's work showing that areas of our limbic system will release dopamine in anticipation of a musical piece that they know is coming, an exciting part, and then other aspects of nuclei in the limbic system will release dopamine at the point at which the musical climax occurs. So, we can see that there is a chemical connection with our reward pathway and music. These are my three beautiful boys. And you know the idea of it's so good to hear the sound of your voice, right? And this is something that we make again and again because of the sound to meaning connections, the repeated ones that we have made with particular voices and particular sounds and our reward system. We looked at musicians and non-musicians and how they processed emotional sounds, and we found that musicians were better able to process the details of the part of the cry that tells you whether the baby means it. And this very simpler portion of the acoustics of the cry actually was enhanced in the non-musicians because that was the only part that the non-musicians were able to really process well. So let me focus on rhythm for just a little bit here, and the idea that rhythm and language coincide. So this is very important for communication. I mean, you know that rhythm exists in music. This will demonstrate that it exists in language.
You're a cheat and a swindler. That's what you are. How can you do a thing like this? Build up a little boy's hopes and then smash all his dreams to pieces. You're an inhuman monster. I said good day.
So here, is another example. This was actually at the Kennedy Center just this last September, where Zakir Hussain, who is...
Zakir, as I'm talking to you now, there is rhythm in my voice. The drums are playing it too. We are here to celebrate the power of rhythm.
So, and the guy back there clapping is Mickey Hart. We talked about rhythm and how important rhythm is for language and communication. Now, simply tapping along to a beat. This kid is pretty good at tapping along to a beat. Here's a kid who is not quite there. Importantly, again, we ask what is happening in the brain. And I said to you before that the rhythms of speech occur. There are rhythms in speech. And if you measure the activity, the brain responses to the rhythms of speech, you will find that the synchronizers follow those rhythms better than the non-synchronizers. And importantly, they have better language skills. So rhythm skills and language abilities coincide. There's a good body of scientific literature to back this up. Again, what is going on in the brain? Well, I can measure your response to sound, and I can see how stable it is. And this is kind of a jittered response. If it's stable, it would look more like this. And we know that neural stability tracks with rhythm skills. We also know that neural stability in response to sound tracks with language skills. And kids who have language disorders have poor synchrony with respect to how sound is processed in their brains. So I want you to listen to Amazing Grace as processed by a healthy brain. And here is a kid with a reading impairment. So it turns out that aspects of sound processing that are especially enhanced with music are timing, different aspects of timing in response to sound biologically, and the processing of the timbre or the harmonics of sound. And these enhancements in sound processing are exactly what underlie good reading abilities. So language skills and sound processing in the brain are very intertwined. And this is an important aspect of how music can help us with communication.
I see a dog. I see a dog. Nice job. I see a dog.
So there is making music, there is music therapy, there is what we can think of as digital music medicine. There are a number of apps and computer games that can enhance our rhythmic skills. We have looked at a particular one called Interactive Metronome, which turns out to be very promising, I think, in terms of building rhythmic skills. And the word interactive is key. So, people are making these movements with their entire bodies, and they are getting feedback. They're interacting with this machine that is telling them, with visual input, how on or off the beat they are. They're also hearing sounds in their right and their left ears. They're giving them auditory cues to make them become better entrained with the beat. And it turns out that interactive metronome tracks quite well with reading skills. Again, what is going on in the brain, I can say that interactive metronome tracks with the brain's ability to follow both fast and slow rhythms with the entrainment that happens biologically that we can see reflected by fast and slow neural synchrony. So, you might want to ask, who's at risk? And the brain can tell us. So by measuring the brain's response to sound, we can predict who might have difficulty reading years before the reading problem happens. And so these would be kids that you would want to recommend rhythmic therapies for, music therapy for. So we know that these aspects of sound processing track with reading in school-age kids, but we also know that if we measure these responses in 3-year-olds, it can predict their language skills when they're 4 and 5 and 6 and 7 as they get older. So auditory motor integration is tremendously important. Again, it is this betweenness that goes between one person and another. It's something that happens between a patient and a physician. And what is important for you to know is that when you are listening to sound that has meaning to you, not only your auditory cortex is active, but so are your motor areas. So in this experiment, Robert Sattore taught his participants to play a musical piece, and then he had them listen to that piece. So after they had learned to play, they were just listening to the piece. They were not moving at all, but their motor cortex was active when they were listening to a piece they had learned to play. And even when they were just imagining this piece of music. So your auditory and motor systems are active. Hearing a noise is tremendously important. People who have learning disorders have particular difficulty hearing a noise. This is a problem after concussion. It's a problem as we get older. And again, we know that people who play music are simply better at hearing speech in noisy environments, like a noisy restaurant or a classroom. What is going on in the brain, you can see it really clearly, that the musician has very strong responses in quiet and noise, and the non-musician has a strong response in quiet, but you can see that he really takes a hit in noise. Importantly, as we get older and we lose our hearing, the audiogram does not tell you everything. It is how your brain processes sound. We can measure how good a person is at hearing speech and noise. They can have a worse audiogram, but they can have musical experience, and they will hear speech and noise better than an age-matched counterpart who has a normal audiogram. And again, you can see this very beautifully in the brain's response to sound. You can see this in MRIs. And I want to just wrap things up here. The idea of rhythm for health, it's important for language, ADHD, autism, dyslexia, movement disorders, aging, concussion. All of these aspects of medicine can be informed by music, and we have biological evidence for this. So biologically, we are what we do. I really encourage you to think about making music for brain health, music therapy, and both with people and digitally. And as Alex mentioned, there is this initiative with the NIH now that has just come out last week with some RFPs to fund music and what is going on biologically, what are the mechanisms. These are the people who work in my lab, which we call Brain Volts. This is the homepage, and I invite you, please, to visit our website and to punch any of these topics if you're interested in learning more. And now it is time for me to invite Mark Lubbers to come up to the stage because art and science are going to join. So what I have done here is we have measured the brain's response to every note on this keyboard. And Mark is going to play the brain.
And Mark is the Director of Student Admissions at Penn State. And I'm just stepping back.
Bear with me. It'll be worth it. You will, if you can play some notes, please. So you will be able to both see and hear. This is the brain. This is the brain processing sound. Keep going, please. You to be able to see it well. Okay, so now I think we're going to do a little bit of jamming, a little jamming with the brain. First, you'll hear just the brain in all its glory.
Bravo, bravo.
The brain keyboard.
Can we have the lights of the house lights a little up, please? Please sit down. Please sit down. Thank you, Maestro. Is there anybody in the house to light up my life? Thank you. So we have a few minutes for questions, and how many people in the audience play an instrument? Whoa, like canoe.
We're preaching to the choir.
How many people are singers? Quite a few.
Singing counts.
So we're going to spend 30 seconds just doing something. Everybody follow me. I can tell lots of musicians in the audience, they were all on pitch. Okay. We have some microscopes where people can talk to. I am going to, I'm blinded by the lights, so I can barely see. but there's a microscope over there, over here, and I think one over here. So we're going to start, we're going to go from right to left, like an ancient language. And please, first question.
Yeah, Quentin Eichbaum Vanderbilt. The data on reading confuses me a little bit, and I wonder whether you can elaborate a little bit about if it's a particular kind of reading disorder, because obviously reading does entail some hearing in the brain or reading aloud. Secondly, how you can use music to improve reading disability. And thirdly, I have a kid who's just diagnosed with dyslexia, and he's very musical and loves music and sings, but I thought dyslexia is more of a visual kind of issue.
So let me just start out by saying, so we learn to speak before we learn to read. And when we learn to read, we are making associations between the sounds that we know in the language and these images on the page. So it's very important that we can hear the sounds well. You ask about different stages of reading, so we can follow language development from pre-reading stages until there are standardized measures of reading. And there have been many, many studies that have shown that sound processing in the brain and the inability to make sense of sound, both biologically and in terms of kids being able to discriminate and make sense of sounds in context. This is something that is often a bottleneck, not in all kids, but in some kids with reading disorders. And there's a good literature. I encourage you, please, to have a look at the studies that have shown that. We have many of our own, and there are many in the literature that we refer to.
So, sorry,
Thank you.
I want to just...
So we're going to gallop right along because we only have a couple of minutes. Please.
Hi, thank you both so much for your presentation here in the center. I'm Callie Ray. I'm a third-year medical student from the Medical College of Georgia, also an amateur musician and artist, and will be declaring pediatric neurology in just a few short months. And I'm very interested in incorporating music into my future practice. So how did you guys end up recruiting participants for your different programs, like drum PD, and did you have a difficult time finding patients interested in music, and how do you recommend that I do that in the future, as I am interested in music and medicine?
So to keep it very short, this is advice I give to all the medical students I have the privilege of teaching. Once you pick a specialty and you want to do research of any kind, clinical research with patients and specifically with music, you want to recruit the patients that you see, the patients you have a clinical relationship with. In my experience, this is what my mentors taught me, this is what I'm passing on, the only way to make a clinical research career nowadays work. And so that's exactly what we're doing. We are fortunate to have a Parkinson's disease center at Hopkins that sees about 2,000 patients. And so there's definitely no shortage when it comes to recruitment. So I have to say though also, I have collaborators at Iowa State, for example, where there's a much smaller center, but there still is no shortage when it comes to these music-based intervention studies. So it can be done in large centers, it could be done in small centers, but most importantly, it needs to be done from within your clinic. So that's the key piece of advice.
Thank you. Regretful we only have time for one more question. I know that many more questions are within the audience. Over here.
Hi, Carl Chan, Medical College of Wisconsin. I was just wondering, you would outline the advantages of musicians in terms of their discriminatory functions and development. And I was just wondering, what happens to these musicians as they lose their hearing?
Yeah, so this is really important. And in fact, there is a pretty orderly and systematic relationship. It's always, it's a balance, right? So on the one hand, if you lose your hearing as you just get older, or please protect your hearing. We're so cavalier about our hearing, even sounds that we think are safe level sounds, like in hair dryers and the subway sounds. Protect your hearing because it will matter. But the fact is that if you are an auditory your ability to make sense of sound is strengthened by that. And obviously, it will be impeded if you have a hearing loss. But again, we have found that, think of Beethoven. We have found that your ability to make sense of the sound that you get, even if it's impoverished, is really strengthened by the experience that you have had making sound and making sound to meaning connections. I also just want to give people another place, another thing to look at. That was your question about how to get people involved in projects. From a medical standpoint, in May, I hosted a music therapy conference at Northwestern because of my interactions with the folks at the NIH. I realized, oh my gosh, there's a whole world of information that I need to learn about. And so I invited the world's experts to come, and they came and they spoke, and we videoed it. And you will find it somewhere on the music page of our website, the entire day worth of lectures, including lectures on Parkinson's disease and traumatic brain injury. So it's a resource for you.
So, ladies and gentlemen, as the end of the opera Pagliacci, la commedia è finita. Grazie.
Thank you.